Hello, everyone. So today we're going to go over classifying drug consumption using a support vector machine. So what exactly is a support vector machine, you ask? So it is a supervised learning model that can analyze data for either classification or regression. And in this project, we specifically used the support vector classifier to perform binary classification, which classifies two different classes from the drug data into users and non-users. So how exactly does a support vector machine work? What it does is it finds the best hyperplane between two classes from the data that maximizes the distance between the support vectors. Now, what are the support vectors? They are the two closest points to the hyperplane, which in this case would be right here and here. So yes, so those are the support vectors. Now, why exactly is this the best hyperplane? Why we choose that? We could have just chosen this or this. This. But we chose this one right here. Specifically, as I said before, it maximizes the distance between these two points, and which are the support vectors. And so in other words, it goes right through the midpoint. So in the picture on the left, that is a linear class that represents linear classification. So the hyperplane is literally a line. But if we had data in higher dimensions, we would use something. We would use a different kernel, either RBF, which represents Gaussian, or polynomial, which projects it into higher dimensional space. And then in that case, the hyperplane is literally a plane, as you see right here. All right. So here's an example which I put in the notebook. So first we imported from the scikit-learn dataset samples the make blobs function. Sorry, that will just generate different data points. And so we had 125 samples and 2 clusters, as you can see from in the graph. And the standard deviation of the clusters was 0.6, and the random state is just 0. That's just for reproducibility. And here is where we split the training and the testing data into these variables: x train, x test, y train, and y test. The reason why the x's are capitalized is because it is more than one dimension, and the y's is just a 1D array, so that's why it's lowercase. And the size of the tests, we just set up the testing data. We set it to 20 points and the random state 0. And then here is where we plotted it, and we fit the classifier over here using the linear kernel and the training data. And as you can see in the image on the right, it produced the red line, which is the best hyperplane between the data. And yeah, so the blue obviously represents one class, and the green represents another class, and the dots represent the training data, and the squares represent the testing data. So this is just the code for displaying the line in 2D. Just like we used a scatter plot, and we just plotted the training data, and then the testing data. As you can see, the marker was S. And then so if you use a linear kernel, the classifier will give you an attribute called coefficients, which is represented by coef, and we just did the math from A to get the variables A, xlim, xx, and yy to generate the hyperplane, and then we just plotted it in red. So that's for your reference. Now let's get on to the project. So the data was taken from the UCI machine learning repository, and this is just a glimpse into the data frame that was used for the features. The features are the input variables, And now, obviously, we did not include ID as an actual feature when training the classifier, because that's not an actual independent variable. So it would just, so the features would just be from age to SS now. So so like obviously the younger ages are represented by the lower numbers, but then in cases of categorical variables like gender, so positive 0.48246 represents female and negative represents male, and the rest, most of these are quantitative. So N is neuroticism, E would be E. So O was openness, A was agreeability, C was conscientiousness, and E was extroversion. So yeah. And here are the labels. The labels are just the drugs, which are the dependent variables. So here was the original data, and then here is the altered data. So on the top, the original data, it's CL. It shows just a bunch of CLs and different numbers that come right after that. So those represent just the levels to which they were used. CL0 was never used. CL1 was used over a decade ago. CL2 was used in the last decade. CL3 was used in the last year. CL4 used in the last month, and 5 used in the last week, and 6 used in the last day. So we separated all of the numbers from 0 to 1 as non-users of a drug, and 2 to 6 as users of the drug. So as you can see, it shows the in the altered data frame the change. So here are the imports we needed. So from scikit-learn, we imported the pre-processing module, the model selection, and SVM, that's the support vector machine. And the metrics, that is just for reporting the data. And obviously matplotlib for plotting the data. So for training and testing. So this is just an example. I'm just going to show you what the process was for classifying the users and non-users of a drug called Amphet. That's just an amphetamine class. So the X was just a NumPy array of all the features. The Y was a NumPy array of the values from the Amphet column. And then here we just split the training and testing data. And then we created the CLF object is the classifier with, as you can see, from svm.svc, and the kernel is linear. And then we fit the training data, and then we got the accuracy by getting the score on the testing data, and then we printed that. And then the Y prediction, that is just for, no, I will show you that later. That's used for the confusion matrix. So for that, we use the clf.predict method, and then we display the confusion matrix. And so, and here we print the classification report. So let's take a look at the accuracy and classification report. So as you can see, the accuracy is around like 99%. That means it's really accurate. And the classification, as it shows, -1 non-user, 1 user. So it's really precise. Like the precision is 1 and 0.99, and the accuracy is also 0.99, and so are the weighted averages. So this is really accurate, and you'll see later just how much. So the confusion matrix. What this is a table that compares the accuracy of a classifier. So it separates the true positives, the false positives, true negatives, and the false negatives. So in this case, we displayed the actual data versus the predicted data. So as you can see, the true non-users, it classified 215 of those correctly, and the true users, it classified 254 of those correctly, and the false users were just 3, and the false non-users, it didn't classify any of the non-users incorrectly. So these are really good results, and ideally the entries along the anti-diagonals, which are the false users and the false non-users, will be 0, but that's pretty hard to achieve. So this is still really good results. And this is just the code for your reference. So you just created a matrix object for from getting the confusion matrix from the testing and the prediction data. And these are just plotting the matrix and the entries. These were true non-users, false non-users, and true users. And then we just stuck the entries as text. Now let's get to how we actually plotted the hyperplane. Okay, so this variable x's, the c-score and n-score, these were just two of the feature variables. These were arbitrarily chosen. So if you go into the notebook, you could literally just change it to any two you even want, any combination of it, but leave the target as the same, because in the notebook is laid out one for each different drug. So that shouldn't be a problem. And then here I just created a function to just well, not really a function, just a loop to just set the classes to equal -1 or 1 just based on the Boolean conditions. And then here we just set up the NumPy arrays. Then we split the training and testing data. We fit it, and then we just set the limit, the Y limit scale, and then just the labels and then the title, and then we displayed it. So let's take a look. So as you can see, really accurate. It separated the two classes along the hyperplane, which is like x equals like some positive number, like close to 0. So if the c-score is less than 0, it will be a user, and if the n-score, and it's not based on the n-score at all, it's specifically based on the c-score. So as you can see, all the users are on the left and all the non-users are on the right. And once again, the circles represent the training data, the squares represent all the testing data. So mission accomplished. We successfully classified all of the non-users and users based on the feature variables for every single drug. As you can see in the notebook, this was just the AMP. This one which you were shown was just the AMP for the AMPHET drug, and which was seen to be really accurate. And so where do you go with all this? So let's see. So we performed our classifications with the linear kernel, and to find but if we ever wanted to find the hyperplane in a higher dimension based on how the data is structured, we would have to use either the RBF, which is the Gaussian kernel, as I said before, which also just happens to be the default kernel, or you can also use the Pauling kernel, and from that you could project it into 3D space, and the hyperplane would literally be a plane. So that's where you can go from this if your data was ever distributed differently. So thank you for watching, and I hope you have a good day.